As I said, Octave is one of the very powerful open source tool environment that can be used for doing control designs. It is an environment similar to MATLAB. Those who have used MATLAB can use MATLAB if you have MATLAB instead of Octave. But those who do not have a license for MATLAB can use this open source tool. Octave is a clone of MATLAB, and any script that you have written in MATLAB can also work in Octave, the .m files. MATLAB has a very powerful controls toolbox, but the controls toolbox in Octave is not as powerful. So we have developed few added tools and functions and installed it as another additional toolbox called the LU control toolbox. It is available, free to be shared, and we will share it in the resources, and then you can use it. There are three important packages that you need to load when you open Octave or when you open your script file. The three important packages are as follows: package load control. You have to load this control. If control is not installed, package install from Forge, or once it is installed, you can always load it every time you open Octave. Package load control and package load signal. This is also another important package that you need. Load that. And as I said, package load LU control. This is the control that we have developed in the lab here, and this is shareable, and then people can use it. We will share it with you. So these three toolboxes are needed, and then before we go into the design using the root locus, few quick getting started tips. So defining transfer functions, I will, for example, if I am having a numerator polynomial, I will say is like this, and denominator polynomial within the vector brackets. Let us say I have the 0.5, 2, like this. So this means that 2, this is 2 into s to the power of 0, 0.5 into s to the power of 1, 1 into s to the power of 2. So that's what it would mean. And if I don't use the semicolon, that will be displayed. For example, if I don't use the semicolon, it will get displayed whatever I have typed. Then if I want to see, let's say the system, okay, I want to see the system, you can use TF, transfer function, numerator and denominator polynomial that we have just typed in. And you will see that this is the transfer function. It will display 1, numerator is 1, 1 divided by s square plus 0.5s plus 2. So this is there in this system C variable. So now let us say you want to see the step response. You can type like this: step system C. Then it'll just be a very bland step response, but you need to give some labeling. So let's say X label within single quotes time in seconds, let us say. Then Y label. Y label can be the magnitude. Then title, can give a title so that the graph looks complete. It's a step response. Step response. So when you click return, so you will see that the plot has been plotted like this. You have the step response, magnitude, time, and this is the step response that you would see. Okay. Let us say I now define a sampling time, TS, some arbitrary, zero 0.5 I will give it, 0.5 seconds. And let's say numerator polynomial in the Z domain, denominator polynomial in the Z domain. And I will use my C to D, continuous to discrete. So the numerator polynomial here is in the continuous, defined for the continuous plant. Denominator polynomial is also the S plane for the continuous plant. And let us say this is the sampling time as I defined 0.5. And I can see what the numerator and denominator polynomial are. I can do that, but this is what you will get. But I would like to represent it something like this in the discrete domain. So I can say sys D, system discrete, TF function, NZ, DZ, and TS, sampling time. So this I can see that you will get in the Z plane, the transfer function in the Z domain. So you have two poles and one 0. If you want to see the frequency plot, so let's say this is C, this is C. You give the omega as log space, let's say -1 to 2, which means 10 to the power of -1 to 10 to the power of 2. Then you bode A, C omega, which will give you the plot of the magnitude and the phase. So these are some of the typical functions that you will use. Other necessary commands we shall learn on the fly. Important thing is that the variables are vector based. So just like you have the integer numbers and real numbers in most programming language, in Octave and MATLAB, a 1-by-1 vector element is the basic building block. Use that concept effectively and you will be able to get very efficient and nice scripts. So let us now begin our controller design using Octave. Let me open a text editor. So I open a text editor here. Let me resize the Octave such that it is next to next like this, where you can see both the text editor on the left and the Octave IDE on the right. So now let us write a simple script, small script on the left in the text editor to display the root locus of a system. So this will become our basic brick for doing the root locus study or root locus design for controllers. So let us do that. So let me the required packages. So package, load, control, package, load, signal, and package, load, LU control. So these are the three packages that we are loading into the system workspace, Octave workspace. And then now we will define the transfer function, the same transfer function which we used earlier. define the transfer function. So the numerator polynomial, pretty simple, is 1. The denominator polynomial is as shown below here. And let us plot the root locus. Now this is the transfer function, and plotting the root locus is simple one-step command. So in Octave, there is something called rlocfind. When the control system toolbox available in the Octave repository, rlocfind is not completed as yet. So I will use from the LU control toolbox, which I have loaded, my rlocfind, and you pass on the parameters, the numerator and the denominator polynomials. So the root locus, this will give you the root locus. So let us do this. There are two ways. Well, let us first save this. I have saved this file as octave_rlocus.m, and I've saved it in the controls examples folder itself, which we are normally using for all the other files. There are two ways in which you can execute this. One is brute force. You just copy all the script lines, take your cursor to the right on the Octave IDE, the Octave environment window, and then paste, and then press return. You will see that the script lines, script codes execute. So you see here that you can put in the grid. You have a figure window here. You have the pole locations. You have 2 poles, complex conjugate poles here. Left off of the zero line, which means they are the poles are stable. So this is the root locus of this continuous domain transfer function as we have seen here. This. Now, what does this my rlocfind do? Firstly, it plots the root locus, and secondly, look at the cursor. Cursor is having a crosshair. You can place the cursor and click on any part of this root loci, and any of the root loci. So it will give out the k gain value at that point where you are clicking the cursor, and also the closed loop pole location. So if you take, for example, this particular root loci, every point is a closed loop pole location, as we have discussed earlier, corresponding to a particular value of gain k. So when you click here, for that same value of gain k, which is at this point, at all other root loci, in this case one more, corresponding value of gain k, it will pick out the poles and display. So that is what k and p is. K is the gain, it will display the gain, and p is the closed loop pole locations at that value. So let us say, for example, here we are having y-axis 2 and the real axis around minus 0.25. So let me click there. So the moment I click there, you see here gain at that point is 2.08 something. And the closed loop pole locations, you have 2 complex conjugate poles, one on this, which is minus 0.25 and plus 2i, minus 0.25 and minus 2i. So you get 2 closed loop pole locations. So this can be used for actually completing the design of your controller through the root locus design. So this is the basic functions that you will be using for the root locus design. We will now use these two, this and this and one more, which I will present to you for looking at the root locus plots and getting out the gain and the closed loop pole location. Now, this is what you have seen here. You can also directly execute this file. So if I go in, let me clear all the variables, clear. So let me go into this location. So you see that Octave or locus, this is the one which is saved. So I am in that particular path. So let me run that, Octave or locus. You don't have to give dot yet. So you will see that it will execute, and this is the plot of the root locus. Okay, so now this is the continuous domain root locus plot. Now, what do you do for plotting the root locus on the Z plane? So that is what we will see next. So let me close this and introduce what I would do for Z plane. So now let us say you have NZ, DZ output. So my C to D, my continues to discrete. So what I will pass, the numerator polynomial, denominator polynomial, and the sampling time TS. So here I need to define TS. So let's say 0.2 seconds. So now here I have NZ dz of the discretized transfer function. So let me pass NZ and dz. So before I do my root locus, I will have to indicate that it is a Z plane. So the plotting has to be done on the Z plane so that you have a background which is Z plane. So for that, a useful function which we have actually prepared and located in LU control is my Z grid. Just that. So my just grid just gives you the background which is the Z plane. So now let us execute this. So let me save that and execute this. So in this one I will run that Octave. So it will convert it into the discrete domain. So you have the background. You see this is the Z plane, the unit circle, and you have the Z plane constant damping ratio low size. You have two poles here and 1 0 here, as we have seen for the same example even in Python, similar root locus plot. So here too I can click anywhere here, let us say, and I will get the gain value and the closed loop pole value. This is within the unit circle complex conjugate poles of these two root loci. So this is how you would do for a discrete transfer function. Now using this basic concept, let us develop the complete program for designing a controller using the root locus method.